Greetings and welcome back. In class lately, we've been looking at different cycloalkanes, particularly focusing on cyclohexane. We've talked about ring flips and how cyclohexanes have axial and equatorial positions, but today we'll be doing something similar to what we did with Newman projections, which is considering which is going to be the most stable conformation under certain circumstances. So, what happens if a cyclohexane has a substituent or multiple substituents? Which chair structure is most stable? That's what we'll be talking about today, so let's jump right in. So first, let's put up the rules that we've already discerned, what we know already. So the first thing we've learned already, and this is based again on looking at those Newman projections, the chair conformations are generally the more stable cyclohexane conformations. So compared to boats, in general, these are more stable. Secondly, there are, for every chair conformation, there's two possible chairs. So for every cyclohexane, we have one structure, and then we can flip it. We do that ring flip where all of the axials become equatorials and all the equatorials become axials. Therefore, there's two different possible chair conformations for every single cyclohexane. And thirdly, that it is more stable for those larger substituents to be equatorial, because equatorial is generally further out in space, further away from the other substituents, rather than axial. And remember, axial turned out to be relatively close to the other axial positions. So let's look at a couple of these structures and reconsider kind of what those two different conformations look like. So these are the two ring-flipped versions of cyclohexane that we saw in class. You'll notice that this is the carbon on the far right that I have ring-flipped. And I've got a bond in green that is on the up position. So it's the higher of the two positions on that far right carbon. And it is, in this case, axial. And when we do the ring flip of this guy, it's still in the up position because it's still the same molecule, but now it has gone to equatorial. And therefore, this is kind of what we see when we do a ring flip, is you take one structure, you flip it to the other ring flip. What's up stays up, what's down stays down, but what's equatorial becomes axial and what's axial becomes equatorial. So let's practice drawing this out the way that we would in class, since we're not usually just going to have pictures. So just like we practiced before, let's start with those center lines. On the one on the left, you can see that we have those two lines that are kind of going down and to the right. And remember, it kind of alternates going up, down, up, down, up, down. And that's how our cyclohexane looks. And let's draw in our axials. So all the up carbons have one sticking straight up, and the down carbons have one straight down. And then for the equatorials, the three carbons on the right have one going kind of off and to the right, and then the three carbons on the left have one going off and to the left. All right, when we flip this, which we'll do before we're going to assign any of our substituents, we're going to do the same thing in reverse. So as opposed to those center lines being down and right, they're going to be going up and right. So kind of like this. Then again, we'll alternate the up carbons. The next one goes down, and then up, and then down, and then up, and then down. All right, and then once again, we'll draw on our axials first. The up carbons have one up. The down carbons have one down. Then there's another one and another one. And then we'll put in our equatorials. Our equatorials are all off to the side. So on the three right ones, they're off and to the right. And on the three left ones, they're off and to the left. All right, and then what we can do is fill in our substituents. So in almost every single position, we have a whole lot of hydrogens. So I'm going to draw those in quickly. H, 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 do, 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 H, H. I bet you thought when we stopped doing Lewis structures you could stop drawing H's, but it's not true. We always have H's in our lives. All right, so going back to that left structure, once again, we had a position that was in the up and axial spot, and so I'm not going to color that as anything specific. Let's just do that we'll just put that as an H, the green H that is. But when we do the ring flip, that guy is still in the upmost position. So on this right-hand carbon, you've got two spots, one that's up and one that's down. When you do the ring flip, up is still up, but it's gone from being equatorial, or sorry, axial, like it is here, to equatorial. So up stays up, but down becomes down. All right, so let's kind of recap this really quickly. So when we do a ring flip, we take what is up and it stays up. What is down stays down. And that's kind of relative. So I will put these in quotations because the upmost stays the upmost. The downmost stays the downmost on each spot. But axial becomes equatorial, and equatorial becomes axial. And we're going to see that for every single time we do a ring flip. And what that's going to do is it's going to help us to discern which conformation is most stable when we start to have larger substituents. So let's move into some examples of that. So this is a relatively simple example in that we only have one substituent, but it illustrates exactly how we would walk through this procedure. So if you're asked what's the most stable conformation of methylcyclohexane, the first thing to do is to draw out methylcyclohexane. So we will draw the cyclohexane first, and I would highly advise that you practice when you're doing this, drawing your cyclohexane or your hexagon with the points off to the right and to the left. That corresponds more closely to our chair conformations when we draw them out. And for a methyl group, we just need to put it somewhere, and the easiest locations are the far right edge and the far left kind of end there. So we're going to just put it on the right. And you have to pick whether you want it to be up or down, because that matters significantly when we turn this into a chair. So I'm going to put it on the up, which is kind of the coming out at you. So we can imagine if we took that thing and pushed it down, that CH3 would be sticking straight up. And the H, on the other hand, would be kind of going backwards, or is in that down position. So I'm going to label those. We're going to say that this guy is in the up of the two positions, whereas the hydrogen is in the down spot. All right. And so now what we want to do is just draw our two chair conformations. They're always exactly the same, and so at this point we're not putting any methyls in. So what I'm going to do is go ahead and do my two lines like this, and I'm going to actually at the same point do my two lines like that. So I can see that I have my two different kind of sloped lines, and then I'm going to fill in the rest. So these are the middle two bonds. So from a down carbon to an up carbon, I'm going to do a down carbon and then up again, then down, and then up, and then down. All right, I'm filling my axials. Up, 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 down, down, down. My equatorials off to the side. All right, and I'm going to do the same thing to my other structure. So this spot right here, upmost, I'm going to go down, and then up, then down, and up, and then down. I'm going to fill in my axials. 3 carbons that are up, I put one up. The 3 carbons that are down, I put one down. Then my 3 equatorials on the left are off and to the side. On the right, they're off and to the right. All right, so that's all my spots. So everything's going to be H's for the most part, except for this rightmost carbon. I'm going to highlight that one in green. So notice because we put the point off and to the right, I have a carbon that's off and to the right here, and a carbon that's off and to the right there. So those are the identical carbons. That's the rightmost carbon, and that's where we have a CH3 in the up position of each. So if you look at these two locations that we have, these are our only two possibilities. The one that's most up is this one, and so that should be where the CH3 is, because we've put the CH3 on a wedge, so it has to be in the upmost position in both cases. So I'm going to write that in. Here's my CH3. And then in the structure on the right, my upmost spot for the CH3 is, it's still up, but now notice that it's axial instead of equatorial. But up remains up, and so my CH3 would be there. Likewise, let's look at the H on that green carbon. The H is located in the down position, and so on this green carbon here again, the H would be in the down position, which is down here, and on the ring structure on the right, it would be in the down position, which is right here. So this isn't straight down, but it's the most down of the two positions we have. So again, down remains down, but axial becomes equatorial. So these are my two ring-flipped structures. Everything else would be H's. I'm not going to fill that in at the moment, but when we're considering what's the most stable conformation, well, the H's don't matter. They're all going to be of exactly the same energy. However, CH3 is a relatively large substituent, and therefore the most important thing is to get as many, or if you can't do that, the largest substituent into an equatorial position, because it's more spread out in space. Electrons repel, they like to be as spread out as possible. Therefore, the most stable conformation would be this one, because the largest substituent is equatorial. And that is it. That's how this works. All right, I'd like you to try one example, and then we'll move into something with multiple substituents and try that. So in this case, we're going to have multiple substituents on a cyclohexane. We have a cis, one isopropyl, and then a 2-methyl cyclohexane. But we're going to walk through the exact same procedure that we did on the previous slide with an easier example. And so the first thing is just to draw out our cyclohexane. Once again, it's really helpful to put the points off to the right and to the left. So let's put isopropyl on 1, and again I'll make 1 the farthest right. It doesn't matter, but I find that it's easier to have either the far right or the far left involved. Those substituents are easier to access. So we'll put an isopropyl coming off to the right. So here's my wedge, and I'll make it an isopropyl group, and then on that position I'll also draw in my H. And on the 2 position, and we'll go clockwise, but you could go counterclockwise and you get the same answer. We would have a 2-methyl, but because it's cis, we need to make sure that the methyl is on the same face as the isopropyl. All right, so both the isopropyl and the methyl are on a wedge. I'm going to draw in my H there as well, going down. Of course, there are H's on this carbon, and this carbon, and this carbon, and this carbon. There's one on a wedge and one on a dash, but I'm not going to worry about drawing those in because this is kind of a line angle structure, and again, we don't usually draw the H's unless we really need to worry about them. And these right here are the only ones we really need to worry about. All right, so that's our structure, and that's what we're going to turn into chairs. So let's draw our chairs, and then we'll fill in the substituents. All right, so up, down, up, down, up, oop, down, and then we will do axial, 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 equatorial off to the side, equatorial off to the side, etc., etc. And these are my 6 positions. I'll do the ring flip, and in the ring flip, I'll make sure that those central bonds are going in the opposite slope or the opposite direction. And then I'll finish my ring off and draw in all of my axials and then all of my equatorials. All right, so now let's fill things in. So once again, I'm going to identify the 2 different carbons. I've got one off it to the right, and that's where my isopropyl will be. And I will indicate that on both of these chairs as well. So that's the off and to the right carbon. Now, the second carbon that has a substituent, I put one spot clockwise from there. And so in my leftmost chair, here's my green carbon that's off and to the right, so clockwise from there would be this carbon. So that I will indicate as well. All right, once again, kind of that right one, which is over here. Here's my green carbon. So the blue would be one spot clockwise of that. So this would be my carbon number 2. All right, and then I'm just going to fill these in. So on carbon number green, carbon number 1, the isopropyl is in the uppermost of the 2 positions. And so when I go down to my chair conformations, I have an upmost and a downmost on the green carbon. So my isopropyl will be in the upmost, and H will be in the downmost. And then I'll do it to the right side carbon as well. I've got an isopropyl in the upmost and an H in the downmost. All right, and then I'm going to do my blue, or my carbon number 2. This one, once again, has the methyl group in the up position. And so the up position on the left structure, which is this one over here, I'm looking at this blue carbon. So I've got one that's more up and one that's more down. Looking on the right structure, I've got one that's more up and one that's more down. So up stays up. I'm going to fill in my CH3 there. And I'm going to put an H on the down. So fill in my CH3, put an H on the down. Because there's a lot going on, I'm going to fill in all of my other hydrogens just to make sure that we are being good. Recall that with line angle structures, a bond that goes off and has nothing written at the end indicates that it's a CH3. So if you don't fill in these H's, then I would assume that this is a CH3, which is incorrect in this case. So I need to go in and fill in all of my H's. All right, so now that we've done this, we didn't get to choose where we want to fill things in. It would be best if everything was equatorial, but note that we don't have that option. So what's really important when you're doing this is you take your structure that you have, which is right here, and then you turn this guy, you decipher this into a chair structure, and then the ring flipped chair structure. So neither of these is perfect in that neither of them have both of your big substituents equatorial. Sometimes you'll have that option, sometimes you don't. In this case we don't, therefore we just have to work with what we have. So in terms of what we have, the one on the left has a methyl axial and an isopropyl equatorial. The one on the right has a methyl equatorial and an isopropyl axial. The most stable place for the biggest substituent to be is equatorial. And therefore, the structure on the left is more stable than the one on the right because of the fact that the largest substituent is equatorial. So the largest sub is equatorial, and therefore this is the most stable conformation. All right, let's practice this one time, and then we will get together in class and practice it some more. So please bring any questions with you, but once again, I need you to practice this as much as you can. Thank you very much, and I'll see you soon.